look, thanks very much for attending this. My idea here is to give my perspective on how we go about considering landscape material fluxes and the role that people have in that across the Holocene. And actually listening to what we've just heard and the questions that have been asked, I wonder about whether I'm stating the obvious here, because we're all hitting the same sort of problems. But anyway, let's see what we make of this. Here we can see the diagram that Maddie showed earlier with the human activities affecting lakes. And thinking in terms of what we can actually measure in the lake sediments, I think the pathways shown on the diagram can be divided really into two classes. There are unique signals, for example, pollutants, toxic substances, things that have come via the atmosphere or through runoff, have the potential to provide unique signals in the sediment record. DDT, bond testing isotopes, microplastics, etc., simply don't occur in nature. Likewise, some pollen types either are new, like cereal pollen, or are in the wrong parts of the world, like eucalyptus pollen in North America, and therefore provide unambiguous evidence that people were around. But not, of course, not all pollutants are like this. Carbon dioxide is a very good example of something which is added to a huge natural flux, even if the isotopic composition is different. And to the left, we see soil particles, nutrients, acids and bases. These are components which are enhancing natural flows. They're not wholly new. And that presents us with a huge problem, because occurring naturally, we're only going to see an enhancement, and where human activity is low or natural fluxes are high, then we're going to have difficulty distinguishing anthropogenic from natural. And this is an age-old debate, of course. The question, of course, is how do we go about tying landscape material fluxes to people? Sometimes it's very easy. And this is an example from California. And it's easy because the Pajaro Valley, in which the lake was situated, was converted from annually burned perennial grasses to European annuals through European colonization of cattle in a very abrupt way. And you can see around 1800, we can see a very dramatic increase in the mineral accumulation rate. And then between 1851 and 1853, gold rush hike in agricultural produce prices meant that we got a switch from pasture to fully ploughed land within 2 years, probably within a year. And we can see that, another tenfold increase in mineral matter accumulation rate in the middle of that diagram. So absolutely nothing subtle about this site. And of course, when you have good sediment records to measure the response, as we have here, and when you have excellent historical information to constrain the drivers, it obviously is quite easy to do this. But obviously that's the exception. In the more distant past, it's more difficult. And I'm just going to run through 3 simple cases of where it's relatively easy, take a look at 3 cases where it's more difficult, and then just reflect on how we might go about approaching it. So this first example, excuse me, my cough, relates to mining production. And the figure on the left we can see is from Brothers Water in the English Lake District, and represents about 500 years of record. And we can see mineral accumulation rates, we can see lead, zinc and copper fluxes. And if there was any doubt about whether these were anthropogenic, and in fact the concentrations make it impossible that they weren't anthropogenic, we actually know that the profiles like this are the same as are recorded on the London Stock Exchange, going right back to the 16th century. So we know that these are anthropogenic signals. To the right is slightly different. It's also a mining record, but it's much older, and it's long transported pollution. And at this lake in northern central Sweden, Kultjärn, the lead has come from Central Europe, 1,500 miles away. Now, in terms of the Roman signal, the one a couple of thousand years ago, there's no clearly associated erosion. And indeed, why would there be erosion? But at some sites, and the one I've looked at, Lilla Öresjön, which I'll mention again shortly, we can see that there is erosion associated with the medieval event. And again, I don't suspect there's a direct connection, but it's the same economic boom. So around 1,000 years ago, for the first time in perhaps 500 years, it became worthwhile to sell grain in quantity. And so even though it's a decade or two later than the lead pollution signal, we get a clear response. So limited documentary evidence here, but good archaeological evidence for the mining, and crucially here, the isotopes mean that we can be confident about the source of that lead. And yes, there is an impact on the environment as well as a human trace. Excuse me. The second case is from Hatchmere in the northwest English Midlands. And here we can see titanium concentration, but we also have titanium flux, showing that we have 3-stepped increases in soil erosion rate. The first 2 of these are associated with ruderal pollen varieties, that is pollen, of course, associated with disturbance, particularly agricultural disturbance. And the second increase is associated with cereal. And given what we know about this area, this pattern is fully consistent with early farming impacts, particularly forest clearance, and likely associated with cattle as well. So another very, very clear signal. And these kind of things are seen throughout the record across Northwest Europe and any other region where we see early farming. So nothing new here. Third example of a clear signal relates to carbon-14 reversals, and this comes from the work of Edwards and Whittington, 2001. I think the Scottish site in Aberdeenshire, we can see a clear acceleration 4,500 years ago, acceleration in accumulation rate associated with the appearance of Plantago, and an increase in Poaceae, a change in forest. And then we get a much more substantial shift about 2,500 years ago, when we get a switch to mineral matter supply as opposed to more general surface soil, and we get a switch to old carbon, showing that we've got a much more fundamental change in the way erosion is taking place. So combining the evidence, of course, we have a very convincing case that this is indeed human activity that's causing the increase in erosion rate. So very strong signals in sensitive environments, direct evidence for people. There can be little doubt that people are involved. But what about cases like this? Here we've got much more subtle signals, and the evidence is much harder to interpret. This is from Lilla Örsjön in central southern Sweden, and just 10 kilometers from the coast. It's studied for its long history of natural acidification. And what we can see is 7,000 years of decreasing zirconium concentrations. That's 7,000 years of catchment destabilization through the early part of the Holocene, excuse me, the greater part of the Holocene. But it ends abruptly 4,500 years ago when that trend of decrease is reversed. There's no archaeological evidence in the catchment, but we do see an association with ruderal pollen and a change in the forest. But there are Neolithic and Mesolithic sites nearby, but we also know at exactly this time, of course, or approximately this time, the climate got cooler and wetter. So it's an age-old problem about whether this is natural. In other words, is this a human trace or not? And you can't easily answer that question. Another example, and this is from Maddie's PhD work, and please ignore the really strong signal at the top there, that's Iron Age, but look instead at the blue lines. They coincide with, they show small bulges in the titanium concentration, which we can expect are related to small increases in erosion rate. And if you look to the Plantago pollen, you can see that the 3 main events have associated Plantago. So that's of course indicating more open woodland, and it's not unreasonable to say then that we've got some indication we have open woodland related to soil erosion. But has this got anything to do with people? And again, it's not unreasonable to suppose that it does. There were Mesolithic people in the area. There are flints found 9,000 years ago at the site, but we can't be sure that that's true. But I don't know what we could do which would actually change this. Excuse me, would allow us to change this from assumption to more to greater certainty. I think even if we found the Mesolithic equivalent of a Coke can in the sediment at the right age, we still wouldn't know whether people caused the openings or whether they simply exploited them. So we have a problem about whether these are human traces or not. My third example is a lovely one from Lac Antoine in the northwest French Alps. And here we see a wonderful record of stability in the early Holocene, erosion towards the end, and there are, as well documented, impacts related to clearance and grazing, and there are well documented changes in climate. And these broadly coincide with the events, but we don't have complete certainty about what it is that's causing these, whether they're human-driven or natural. So what can we do about this? How can we go about distinguishing natural from anthropogenic when it comes to material fluxes in the landscape? In this hypothetical case, we can see nice parallel records of soil erosion as a response variable, cereal pollen, perhaps charcoal, as an indicator of human impact. And for this nice hypothetical example, we've got a direct archaeological evidence for the presence of people in the catchment. So what do we know from that? Well, we have unambiguous evidence of agriculture in the catchment, and we know that that's associated with enhanced soil erosion. But is that proof of cause? Well, if we add to that some modelling work, in other words, if we can show that a modelled land cover and a simple model of erosion suggest that the expected human driver could indeed lead to that sort of change in erosion, then we're reasonably confident that enhanced soil erosion is consistent with catchment agriculture as the main driver. And I suspect that's as close as we're ever going to get to proof. But things are rarely as clear as this. And how confident will we be of that if we didn't have the archaeological evidence, for example? To what extent is this simply an assumption? And then we have this case. Now we've got a case pretty much like the Mesolithic examples in Britain, with ruderal pollen or charcoal associated with the soil erosion. We've got evidence in this hypothetical case of people in the catchment. So we've got definite evidence of opening of the landscape and being associated with erosion. But actually, we can devise natural and anthropogenic scenarios to explain this record, and so we can't be sure which is which. So the problem may simply be that we've got an individual site here and we cannot be certain, and maybe we never can be certain at exactly this site whether people are the direct cause. But if we look instead at a regional case, and of course this looks identical, it's the same diagram, we have a slightly different situation. Excuse me. We still haven't got proof of cause, but we have perhaps got a greater basis for generalization. In other words, within the region, we have higher erosion associated with the presence of people. Erosion is higher when people are present in the landscape. And that means we can start making assumptions. If we assume a causal relationship, then we can calculate the sediment yield that takes place during that period of assumed human activity. And we can apply modeling methods to test that for plausibility. And that means we can start to ask questions. Excuse me. We can start to frame questions which are useful questions about the catchment functioning, and those questions can lead us to improve our overall knowledge, and that can lead us to a further question, then a refinement of the assumptions that we're making. In other words, if we move from the case to the region, we get more possibilities in terms of understanding what's going on. And I'm going to give an illustration of that. And of course, we had saw an illustration earlier on with Mohammed's discussion of meta study of carbon. But the example I'm going to show here is from Maddie's PhD work. So the paper describing this is now online. I should point out Maddie submitted her thesis last week, so this is hot off the press. And if you click on the QR code down there, you'll get a link to the paper. It shows what can be done if we attempt a regional integration. And here the regional integration is using reconstructed past lake water total phosphorus concentrations and catchment yield based on a novel geochemical method, which I won't describe for the sake of the time. Top left map shows the 24 published records, and these are published records that have sufficient information to apply the model to calculate TP. And below that, we can see the cumulative, excuse me again, cumulative across the Holocene, cumulative phosphorus yield from the catchments. Managed science used to break down into 3 distinct shapes, although there are ones which are intermediate between those. And those 3 distinct shapes, which he terms traits, are trait 1, exemplified by Sargent Mountain Pond in Maine, shown in the top in the middle there, where phosphorus yield was highest at the beginning of the record and then tails away more or less exponentially. And consequently, we get a convex upwards cumulative curve. And this is typical of what you'd expect in a reset landscape with only natural processes operating. Case 2, trait 2, is illustrated here by Antern. And here we get, relatively speaking, low fluxes yields at the beginning of the Holocene, and then stepwise increases during the middle and later. And at most of the sites, in fact, all of the sites where agriculture is present, we find this trend. We have early agriculture present. And the third type, illustrated by Hatchmere, and as illustrated by Hatchmere, often occurring at trait 2 sites as well, we get a recent acceleration. And this is where sites we have recent human activity, particularly recent human settlements, new towns, and that kind of thing. So what can we do with these? These can be used to generalize. And if we look to the top right there are the density diagrams, which I won't do justice to at all. They're divided by trait and divided into time periods, and with phosphorus yield above and total reconstructed lake water total phosphorus below, we can see that we get we can make broad generalizations, and these generalizations can be used to infer changes in phosphorus yield from the landscape to the sea, for example, and they can also be used to predict expected total phosphorus concentrations in the past, and therefore a basis for lake management today. Excuse me. Now, what I did say is that the traits here tie in broadly with archaeological evidence. It's not something we particularly emphasized because we didn't specifically search that information. Could it be tied in better? Perhaps all we need for that, of course, is a suitable human traces database. And that, of course, is indeed why we're all here. So to summarize all of that, clearly that was a very Northwest European perspective. But I do think it has much wider application, albeit, of course, with a different take on appropriate regions, regional subdivisions, and obviously perhaps some new traits. And for example, trait 1 is only going to be present, is mostly going to be present in recently deglaciated landscapes, and therefore won't spread across the whole world particularly well. Excuse me. But I think the key to this, as I see it, is, well, three things are key to this. And the first thing is what this Human Traces project is all about, which is integrating human archaeological evidence with good lake sediment records and simple process modeling. And we need all of those. The process modeling is an essential part of showing some kind of process realism in there. It makes sure that what we are finding makes physical sense. We need, of course, good lake sediment records, which I don't need to emphasize too much here. And then we got the importance of integrating with archaeological evidence. Those sites where we have clear evidence of the presence of humans, it's much more convincing that our small increases in erosion rate, for example, are indeed associated with people or caused by people. But this is much more easily implemented at a regional synthesis than it is at individual sites. Why? Because we know that the records are sporadic, lakes don't occur everywhere, archaeological sites aren't found everywhere. That doesn't mean they aren't present, but they haven't been located. So if we take a regional view, we have a better chance of integrating this information. I do what I emphasize here, I'm not suggesting we stop focusing on individual records. They are, of course, essential. They are the building block on which a synthesis can take place. But that a regional synthesis provides a level of information which can't be provided by an individual site. And indeed, it can be used to aid in understanding regional individual site variations. And the final thing I think which is essential, sorry about this, is to frame questions as scenario testing rather than reconstruction. And this is very much the idea. I mean, I've thought of this a long time, but it goes back to, for example, how reveals is constructed. An individual pollen diagram can't be used to reconstruct a unique landscape. There are just too many mismatches in there and too many possibilities. But the reverse is true. If you have a particular scenario, it leads to a unique pollen profile. So at least in a modeling world. So that means that if we have ideas about what is happening in the landscape, we can test those, if we have respectable models, we can test those against our lake sediment records. And that is a more fruitful way forward than attempting to apply reconstructions. Right, I think I'll leave it there. So if there are any questions, please fire away. But I'm very well aware that we are now past time, well into our break. So yeah, I'm happy to take some questions now, or we can take them a little bit later after we've had a break and perhaps do that during the discussion.